So what's the smartest way to build a network? Whether you're laying down internet cables, designing a power grid, or even just planning out delivery routes, the same problem always pops up. How do you connect everything together using the least amount of, well, stuff? Today, we're going to solve that problem.
Just imagine for a second that you're in charge of this massive project. You've got a dozen cities, maybe even 100 servers, and they all have to be connected. Now, you could just run a cable from every single city to every other city, but wow, would that be expensive. You'd be blowing the budget on day one. The real goal, the smart goal, is to connect everyone using the absolute minimum amount of cable. Finding that perfect, most efficient layout, that's the real puzzle.
So the first piece of this puzzle is something called a spanning tree. Let's forget about being efficient for just a minute and focus on one thing: connecting the dots. A spanning tree is basically any network that links up all of our points, or vertices as the tech folks call them, without creating any weird redundant loops. It's the simplest connection possible, and it follows a few very important rules.
Right, so every single spanning tree abides by 3 golden rules. First up, it has to connect every single point. No city left behind. Second, it's super efficient with its connections. If you have V vertices, it uses exactly V-1 edges. Not one more, not one less. And third, and this one is absolutely crucial, no loops. You can't start at one city, follow the cables, and end up right back where you started without retracing your steps. That's a cycle, and in a spanning tree, they're forbidden.
Okay, so a spanning tree connects everything. Got it. But here's the thing, for any group of cities, there can be tons of different spanning trees. So which one do we pick? Well, that's where the minimum spanning tree, or MST, comes into play. It's the one special spanning tree where the total length of all the cables, or the cost, the time, whatever weight you're measuring, is the absolute lowest it can possibly be. This is our holy grail, the cheapest, fastest, most efficient network we can build.
So how do we find this magical MST? Let's meet our first method, Kruskal's algorithm. The best way to think about this one is what I call the thrifty shopper method. Imagine you have a catalog of every possible connection you could make, with a price tag on each one. Kruskal's algorithm is like a shopper who goes through that catalog and always picks the cheapest item available first.
The strategy here is brilliantly simple. Be greedy. You just look at every single possible connection across the entire map, you sort them by price, and you always pick the cheapest one you haven't picked yet. That's pretty much it. But there's one critical rule you have to follow. You can never, ever add a connection if it creates one of those forbidden loops.
Let's walk through it. First, you take every single possible cable and you make a list, sorted from cheapest to most expensive. Then you just start at the top. Pick the number 1 cheapest cable. Does adding it create a loop with what you've built so far? No? Awesome. Add it to your network. Move to the next cheapest one. Does this one create a loop? Yes? Okay, toss it out, move on. You just keep doing that until you have V-1 edges, and believe it or not, you've just built a perfect minimum spanning tree.
Okay, wait a minute. That raises a huge question, right? Checking for cycles sounds complicated. As our network gets bigger and bigger, how can we possibly know instantly if adding one more cable will accidentally connect 2 cities that are already connected through some roundabout path? Doing that by hand would take forever.
The answer is a really clever data structure called a Disjoint Set Union, or DSU. Think of it like a lightning-fast team manager for all our cities. At the beginning, every city is on its own team and its own little group. When we add a cable between 2 cities, we just tell the DSU to merge their teams. So before adding any new cable, we just ask the DSU one simple question. Hey, are these 2 cities already on the same team? If the answer is yes, we know that cable would create a loop, so we skip it. If the answer is no, we add the cable and merge their teams. It is an unbelievably fast way to avoid those cycles.
All right, on to our second method, which takes a totally different approach. This is Prim's algorithm, and I like to call this one the steady builder. Instead of bargain hunting all over the map like our thrifty shopper Kruskal, Prim starts in one place and just grows. It methodically expands its network one connection at a time.
The logic here is also greedy, but it's a different flavor of greedy. You start with any single city, doesn't matter which one. Then, you look at all the possible cables leading out from your tiny little one-city network. You pick the absolute cheapest one that connects you to a city you haven't visited yet. Now your network has 2 cities. You just repeat the process. Find the cheapest edge connecting your 2-city network to the outside world, grab it, and keep growing.
It's kind of like conquering a map. Step 1, plant your flag in any city you want. Step 2, find the cheapest possible bridge that connects your current territory to a new, unconquered city. Step 3, you build that bridge, and now that city is part of your network. And step 4 is just do it again. You're always expanding your border with the cheapest possible link over and over until every single city is flying your flag.
So we've got two brilliant greedy algorithms, the thrifty shopper and the steady builder. And they both give us the correct minimum spanning tree every single time. So which one should you actually use? Well, that really depends on the kind of network you're dealing with. It's all about choosing the right tool for the job.
So here's the breakdown. Kruskal, our thrifty shopper, is perfect for what we call sparse graphs. Think of a network of rural towns where there are only a few roads connecting them. Primes, the steady builder, really shines on dense graphs where almost everything is connected to everything else, kind of like the complex circuits on a computer chip. So the takeaway is pretty simple. The shape and density of your network tells you which tool to grab. And for those of you who geek out on performance, here's the quick version. Kruskal's big task is sorting every single edge at the beginning, and that kind of sets its speed limit. Prim's, on the other hand, just has to keep track of what the cheapest next step is from where it's currently standing. So in those really dense, messy networks with a ton of connections, Prim's is often faster because it doesn't have to look at the whole map at once.
Now, as you start using these, watch out for a few common traps. With Kruskal, if you forget to check for cycles, your thrifty shopper is just going to create a tangled, inefficient mess. And for Prims, remember it only grows from where it starts. So if your network is made of two separate islands of cities that aren't connected, Prims will only build a tree for the island it started on. It won't see the other one at all.
So, let's just boil it all down. A minimum span tree is the cheapest way to connect all the dots, period. Kruskal's algorithm does this by thrift shopping for the best deals across the whole map. Prim's does it by steadily building outward from one starting point. Neither one is better. The right one to use always depends on the type of network you're trying to build.
And there you have it. You now have the fundamental tools to solve a huge class of optimization problems. Seriously, the logic of finding a minimum spanning tree can be applied to circuit design, supply chain logistics, even some types of machine learning. It's an incredibly powerful way of thinking. So the only question left is, now that you know how to build the most efficient network, what complex system are you going to simplify next?